Light can behave as two different entities. It has dual nature. It has wave nature and it has a particle nature, meaning that light can propagate as a wave, as it's shown in the figure above, or light can behave as a particle as it's shown in the schematic below. And the particle nature of light in that case is actually related or attributed to the existence of photons. However, in our case today, we are going to be studying solely the wave nature of light, but more specifically, we are going to be studying the interference and the diffraction of light. Let's start with the case of interference. Interference can be divided into two major categories. We have the completely constructive and completely destructive interference. In the case of the constructive interference, we are going to consider over here that we have two light waves that are traveling in the same direction. Now, if these two waves are perfectly synchronized in such a way that all of their crest and all of their trough are actually located on top of each other, moreover, these two waves are intersecting each other at the same x values, therefore, these two waves are said to be in phase, meaning they have the same wavelength. Therefore, these two waves are going to interfere constructively, meaning that they are going to add up and they are going to form a new wave which has a much larger amplitude. And therefore, the amplitude of that new wave would be equal to the sum of the amplitudes of the two interfering waves. So A would be equal to A1 plus A2. Moreover, if we have over here a viewing screen, therefore these two interfering waves are going to be showing over here the formation of a bright fringe or simply a bright spot on that viewing screen, which is an indication that these two waves are interfering constructively. Now moving on to the destructive interference. Over here now we have two waves, two light waves that are still traveling in the same direction. However, these two waves, first off, they have the same amplitude. In addition, the crest of the first wave is opposing the trough of the second wave and vice versa. Moreover, these two waves are intersecting each other along the same x values. Therefore, these two waves are said to be completely out of phase, meaning that these two waves are going to interfere destructively, so they are going to cancel each other out. So in that case, we don't have the formation of an amplitude. The amplitude now is vanished, but rather now we have sort of a straight line, meaning that these two waves cancel each other out. So if you have a viewing screen over here, on that viewing screen we are going to have the formation of a dark fringe or simply a dark spot, which is an indication that we have destructive interference. And basically what's happening over here that the red wave, it has shifted by lambda over 2 with respect to the blue wave. So over here, if we have a look at the crest of that red wave, if we shift that wave from this position to that position over here, meaning that we have shifted it by lambda over 2. So over here we have a lambda over 2 phase shift between these two waves. So that phase shift of lambda over 2, it caused these two waves to interfere destructively with each other. Now how can we translate these two phenomena, the constructive interference and the destructive interference, in our topic of today? Let's begin with a double slit interference over here, or simply we can refer to it as Young's double slit experiment. So over here we have a light source which is illuminating two narrow apertures, A1 and A2. An aperture is basically, it's a small opening which allows the passage of light. So over here A1 and A2, they are two identical apertures, meaning that they have the same separation, the same slit separation. And since over here we have a light source illuminating these two apertures, therefore A1 and A2 are going to act as two coherent light sources. Now facing these two apertures over here we have a viewing screen which is located at a certain distance d. But moreover, that distance d over here is actually too big in comparison to that separation d over here between these two apertures. So these two apertures are separated by a certain distance d, but moreover that separation between slit and screen is actually too big in comparison to the separation between the slits. Now, if we consider that point over here, which is actually located halfway in between A1 and A2. So over here that point is actually located halfway in between, almost halfway in between A1 and A2. In that case, at that point over here we are going to have certain type of interference. So we have waves of light that are emerging from A1 and A2. They are traveling along a certain distance and interfering at that point over here. However, these two waves of light that are emerging from A1 and A2, they are traveling along the same distance r. So that wave is traveling along a certain distance r, and that wave over here is also traveling along the same distance r. Therefore, these two waves are going to interfere over here constructively, meaning they are in phase. So they are going to add up and form a new wave of a much larger amplitude. And on that viewing screen, this is actually showcased by the formation of a central bright fringe. So these two waves are going to interfere constructively over here, and as a result, over here we have the formation of a central bright fringe. Now, if you move away from that central bright fringe, whether up or down, therefore, the waves of light that are emerging from A1 and A2, now they are traveling along two different distances. So in that case, we have a path difference between the waves that are coming out of A1 with respect to the waves that are coming out of A2. And in that case, that path difference is going to lead to a phase shift between the two interfering waves. And that phase shift, therefore, is going to cause the waves to either interfere constructively or destructively. So when we move away from that central bright fringe, whether up or down, we are going to have the formation of a successive dark fringes and bright fringes. So if we look over here, first off, we have a trough. The trough, it corresponds to a minima which is a dark fringe, meaning that we have a destructive interference over here between the wave coming from A1 and A2 and interfering at that point. Then that minima over here is followed by another bright fringe where we have now a constructive interference followed by another dark fringe followed by a bright fringe, etc. And the same thing for the pattern below, which is going to be identical to the pattern at the top. So over here we have a dark fringe followed by a bright fringe, another dark fringe, so on and so forth. Now, how can we predict in a mathematical manner or in a more accurate manner what the interference type is going to be along that viewing screen? So we are going to consider over here a certain point P. And at that point P we have an interference of light between the waves that are emerging from A1 and A2. Over here we have a wave of light emerging from A1 and directed toward that point P. And over here we have a second wave which is emerging from A2, from aperture A2, and directed toward that point P where interference is going to happen. So in that case, light which is emerging from A1 is traveling along a certain distance R1, and light emerging from A2 is traveling along a certain distance R2. Now, like I said before, when we move away from that central bright fringe, therefore these waves of light are going to be traveling along two different distances. So we have a phase difference or a path difference between them. In order to determine that path difference, all we have to do is taking the perpendicular from A1 onto A2. So from that point over here, from the aperture A1, we are going to take the perpendicular onto A2. And therefore that portion over here, that segment over here is going to refer to delta, which is none other but the path difference between these two waves, meaning that the wave which is propagating from A2 and traveling along a certain distance R2 is traveling an extra path length of delta with respect to R1. Now in that case, to find an expression for delta, we are going to consider that angle over here to be a certain angle theta. Therefore, by applying trigonometry, sine theta would be equal to the opposite segment, which is delta, over the separation between these two apertures, which is d. Therefore, delta is equal to d times sine theta. Now, if that path difference over here is actually proportional to lambda, or to 2 lambda, or to 3 lambda, meaning that the phase shift between these two waves over here is lambda, or 2 lambda, or 3 lambda, or 4 lambda, therefore these two waves are going to interfere constructively. So, if delta, which is the path difference, is actually proportional to lambda, or 2 lambda, or 3 lambda, or 4 lambda, so on, meaning that the phase shift between these two waves is actually lambda, or 2 lambda, or 3 lambda, or 4 lambda, therefore we have a constructive interference between these two waves. And therefore, delta would be equal to m times lambda, where m over here would be an order, and m would be equal to 1, 2, 3, 4, 5, so on, etc. Now, the second case is if that path difference over here now is proportional to lambda over 2, or 3 lambda over 2, or 5 lambda over 2, therefore these two waves are going to interfere destructively. So, if delta now is proportional to lambda over 2, or 3 lambda over 2, or 5 lambda over 2, so on, therefore we have a destructive interference, meaning that over here we are going to have the formation of a minima, formation of a dark fringe, while over here we are going to have the formation of a bright fringe, and therefore delta would be equal to m plus half lambda. Now in our case today we are going to be solely studying the case of constructive interference, so we are going to proceed with that equation over here, delta equal to m lambda, where m is equal to 1, 2, 3, 4. Now in order to understand better why a phase shift of lambda, 2 lambda, or 3 lambda is going to yield the constructive interference, over here, if we go back to that pattern, let's say we are shifting that blue wave by lambda. So we are shifting the position of that blue wave from over here until over here. That corresponds to lambda. Therefore, as we can see, the crest of that blue wave is still above the crest of the red wave. Therefore, these two waves are still going to interfere constructively. Now, let's say we are shifting it by 2 lambda. So we are shifting it from that position to that position over here, which corresponds to 2 lambda. Again, the crest of that blue wave is still above the crest of the red wave. Therefore, these two waves are still going to interfere constructively. But however, as we move away from the central fringe, as we can see that the intensity of the pattern is actually dropping down, simply because now the phase shift is becoming bigger and bigger between these two waves. So let's carry on with that expression over here. So we have established that delta is actually equal to d sine theta, and delta is also equal to m lambda. Therefore, m lambda, or d sine theta, is equal to m times lambda, where m is equal to 1, 2, 3, 4, 5, so on, etc. And that would be the equation of the angle to the maxima in the case of an interference pattern. So that would be the equation in the case of a constructive interference. So over here we have the equation for the angle to each bright fringe and the interference pattern. Now we need to get rid of that angle over here, since our target is not in finding the angles, but rather it's in finding the separation between two consecutive minima or two consecutive maxima. So if we go back to that schematic over here, we can consider the following right triangle, which consists of that separation over here between slit and screen, which is D, and over here we have that distance y, which is separating the center of the central bright fringe from the point at which we are determining that constructive interference, and we refer to it as y. And then over here we have the following segment, which is relating that point P to the center between A1 and A2. So we have that following right triangle over here, which consists of that segment of y and of the separation between the slit and screen. And over here we are going to refer to that angle as theta prime. So by applying trigonometry in that right triangle over here, we can find that tangent theta prime is actually equal to the opposite segment over the adjacent. So y over d. So tangent theta prime is equal to y over d. However, over here we have a condition which we have already set. That is, the separation between the slit and screen is actually too big in comparison to that separation between these two apertures. In that case, these two angles over here are extremely small, so they can be equated to each other, meaning that now tangent theta prime is actually equal to sine theta, which is equal to theta, which is equal to y over d. So over here we can approximate the tangent to be equal to sine, which is equal to theta, which is equal to that fraction y over d, simply because d is too big in comparison to the separation between these two apertures. So therefore we have two extremely small angles. And therefore that equation over here becomes d times y over d is equal to m times lambda. Therefore y is equal to m times lambda over d times separation between the slit and screen. And that would be our final equation in the case of the constructive interference. Now what is y over here? Y is not going to be the same as that y that we have defined over here. Because whenever we have two apertures or more than two apertures interfering with each other, or light coming from two apertures interfering from each other, therefore the interference pattern that we are going to obtain is going to be much more complicated than this one. The interference pattern is going to resemble the following. So over here, as we can see, that central bright fringe in the case of an interference is actually being divided or being split into multiple small bright fringes, multiple small maximas. So over here we refer to each peak as a maxima or simply as a bright fringe. So as we can see, the central bright fringe is being divided into multiple small bright fringes simply because we have an interference. We have an interference of two apertures, of light coming from two apertures. And the same thing for the bright fringes on the right and left. Each bright fringe now is being divided into several small bright fringes that we refer to each one as maxima, or we can refer to it as a peak. So in that case, what we are actually finding either the separation between two consecutive maximas or the separation between two consecutive minimas, which is actually the same, since over here these separations are equal. So that y that we have established over here, the equation of y, that equation of y that we have established over here is going to be for the separation between two consecutive maximas or the separation between two consecutive minimas. It's not going to matter since the separation is going to be the same for both in that case. So what we are actually doing in that case, we are measuring the width of that central fringe. Let's label the width to be W. So after labeling the width, after measuring the width, now you are counting how many maxima do we have within that central bright fringe. So let's say over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So let's say we have 18 maxima within the central bright fringe. Therefore, after calculating the width of that central bright fringe, you divide the width by 18, and therefore you have y, which is going to be the separation between the consecutive bright fringes or the consecutive minima. So after finding y, we have the order. The order in that case is going to be always equal to 1. Since right now we are not operating in a certain bright fringe with respect to the central one, but rather we are considering each bright fringe to be a sole entity, to be a separate entity. Therefore, the order is going to be 1 for all fringes. So initially, if we wanted to define these orders over here, we are going to refer to that central fringe to be m equal to 0, while over here the center of the first fringe on the right side to be equal to m equal to 1, and over here the center to be m equal to 2, so on and so forth. And the same thing for the part below. Over here we have m equal to 1, over here we have m equal to 2, etc. However, since in that case we are working within each fringe separately, therefore we are considering each fringe to be a separate entity. Therefore the order is going to be 1 for all fringes. So m is equal to 1 always in all cases. And d would be the separation between the two apertures, and d over here would be the separation between the slit and screen, and therefore our unknown is going to be the wavelength of the laser light, which is going to eliminate these two apertures. So having y, having d, having m, and having the capital letter D over here, we can determine the wavelength of that laser light. Then the same thing is being repeated for that fringe on the right side. So also you measure the width of that fringe over here, let's say it's W prime, then you count the number of maximas within that fringe over here, you divide W prime by the number of fringes, and you get the separation between two consecutive maximas or the two consecutive minimas. And then you determine the wavelength of the laser light all over again, which is going to be compatible with the previous parts. The wavelength is not going to change whenever we are maintaining the same medium, which is free space medium. Now moving on to the case of diffraction. In that case, we have a light source that is illuminating only a single slit. And that slit over here, it has a certain width or a certain slit separation, which is denoted as W. And over here we have the screen, which is located at a certain distance d from the aperture, noting that the distance between the slit and screen is actually too big in comparison to the width of that aperture over here. Now what is actually diffraction? Diffraction is basically the bending of light. So whenever light passes through a very finite aperture, light is going to undergo bending. So for example, if we consider over here the following aperture which is being illuminated by light, therefore light which is going to emerge from that aperture is going to undergo bending. However, it's going to also spread out as it propagates. So diffraction is basically the tendency of light to pass through a finite aperture and to spread out as it propagates. However, in order for diffraction to be applicable, the width of that aperture should be larger than the wavelength of the light beam. Otherwise, the diffraction pattern is not going to be observed. So if that slit over here is too large or it's too big in comparison to the wavelength of the light beam, therefore light is going to simply emerge through without undergoing bending. So it has to be slightly larger than the wavelength of the light beam in order for diffraction to occur. Now, moreover, diffraction, it actually involves a special kind of interference, which is called mutual interference or simply self-interference. And that phenomenon was described by Christian Huygens in his famous principle, who stated that when a wave of light reaches the aperture, that wave of light can be divided into several portions, into several points, meaning that we can distinguish several points along that wave of light. Therefore, these points, when they reach the aperture, they are going to be the source of a new wavelet of light. So, let's consider over here, we have the following aperture, and we have the following waves of light reaching the aperture. Christian Huygens basically said that each wave of light, we can distinguish on it several points. Therefore, when that wave of light reaches that aperture over here, these points are going to be now the source of a new wavelet of light, meaning that each point is going to generate a new wavelet of light. Therefore, these wavelets of light, as we move away from the aperture, they are going to spread out. However, once they are spreading out, they are going to interfere with each other, and hence we have an interference pattern within the diffraction model over here. So the diffraction model, it also involves an interference model or an interference phenomenon. So in that case, due to these interferences between the wavelets of light, over here we are going to obtain the following diffraction pattern, which consists of multiple dark fringes and bright fringes. So over here at the center, we have the central bright fringe, which is followed by a dark pattern or a dark fringe over here, which is represented by the trough. Then over here we have another bright fringe, followed by another dark fringe, so on and so forth. And the same thing below. It's actually an identical pattern to the one at the top. So let's consider over here at that aperture that we have the following points, which are actually located on a wave of light that approached that aperture over here. Now, in a similar manner to what we have done before, we need actually to try to predict in a mathematical manner, in a more accurate manner, what type of interference should we get over here along that viewing screen. So let's consider that first point over here, which is a source of a wavelet of light, is going to interfere at a certain point P over here. So we are going to consider that point P over here, where a wave of light which is coming out from that point and the wave of light which is coming out from the middle point are both going to interfere at that point P over there. So we have the first wave of light which is propagating from that first point toward P and traveling across a certain distance r1, and interfering with another wave of light which is propagating from the middle point on that aperture and interfering at point P. And that wave of light over here is traveling along a certain distance r2. Like I said before, since we have two waves that are traveling along two different distances, therefore these two waves might interfere either constructively or destructively depending on the path difference between them. So in order to determine the path difference, we are going to revert to the same method that we have done before by drawing the perpendicular from that first point onto R2. And therefore that stretch over here, that segment, would be referred to as delta, which is none other but the path length difference. Therefore, over here we can distinguish a certain angle theta. Therefore, by applying trigonometry, sine theta would be equal to the opposite segment delta over the hypotenuse, which is none other but that width w over 2. So that stretch over here, that part, corresponds to w over 2. Therefore, sine theta is equal to delta over w over 2, so delta over w times 2. Therefore, delta would be equal to omega over 2 times sine theta. Moreover, since at that point P over here we have a destructive interference, meaning that the phase shift between R1 and R2 is actually proportional to lambda over 2. So delta in that case is actually proportional to m times lambda over 2 without specifying the order. We don't know the order at P over here. So we are going to leave it as m times lambda over 2. So again, since over here these two waves are interfering at point P where we have a destructive interference, where we have a dark fringe, therefore the phase shift between that wave and the other one is actually proportional to lambda over 2. So delta is proportional to m times lambda over 2. Therefore the equation becomes delta equal to w over 2 times sine theta, which is equal to m times lambda over 2. Therefore w times sine theta would be equal to m times lambda. And that would be the equation of the angle to each dark fringe along that diffraction pattern. So over here we have the equation of the angle to each dark fringe, or let's call it to each minimum, on the diffraction pattern. However, the purpose in our case today, the purpose in that part is actually to determine the distance from the center of the central bright fringe to each minima, to each dark fringe, meaning we need to determine the distance from that center over here to that first dark fringe, which we are going to refer to as order m equal to 1. So that would be y. Then we need to find the distance from the center of the central bright fringe to m equal to 2, which is the second minima on the right side, which we refer to it now as m equal to 2. So that would be over here y prime. Then also the distance from the center of the central bright fringe to m equal to 3, which is the third minima over here. So let's call that y double prime, and over here we have m equal to 3, so on and so forth. And the same thing below, but it's going to be identical. So after obtaining these y values over here, we need to determine now the wavelength of the laser light. So in order to obtain the wavelength, that equation over here should be adjusted. We need to get rid of that sine theta over here. So we are going to consider the following right triangle. Which consists of that segment and which consists of that stretch over here, which we denoted as y prime, which is going to be the distance between the center of the central bright fringe to m equal to 2 over here, which is none other but y prime, and then over here which consists also of r2. Therefore, tangent theta prime would be equal to, so we are going to call that angle over here to be theta prime. Therefore, tangent theta prime would be equal to the opposite segment, which is y prime, over the adjacent, which is none other but the separation between slit and screen. But again, since the separation between the slit and screen is too big in comparison to that slit width, therefore these two angles, theta and theta prime, they are extremely small angles. Therefore, the tangent theta can be approximated to be equal to sine theta, which is equal to theta, which is equal to y prime over d. Therefore, that equation over here becomes w times y prime over d is equal to m times lambda. Therefore, y prime is equal to m lambda times the separation between slit and screen over the slit width. And that would be the final expression in the case of diffraction that we are going to use. Where y prime, like I said, or simply y, let's call it y. y is going to be the separation or the distance between the center of the central bright fringe to each minima, to each dark fringe, to m equal to 1, to m equal to 2, to m equal to 3, to m equal to 4, etc., so on and so forth. So after having the value for that separation between the central bright fringe to each minima, you plug it over here, you have the order. The order can either be to m equal to 1, or to m equal to 2, or to m equal to 3, so the order is going to vary with each trial. The slit width is always a constant, it should be given, and then you have the separation between the slit and screen, and therefore the unknown would be in that case that wavelength lambda over here, which we need to determine. And lambda, like I said before, it should be constant for all trials, since that laser light is actually propagating in free space, so the medium of propagation is not changing. Even whenever we vary that order over here, that wavelength should not vary. The wavelength of the laser light should always remain a constant. And that would be it for the interference and diffraction.